Graph the function. All right, so we have a rational function here. In order to graph it, we have to follow a several-step procedure. Really, this is the kind of thing that software is better at than humans doing it by hand. But let's go ahead and just actually follow some steps to get a good sketch of the graph going. So let's start with the first step, which is to factor the rational function. So we're going to factor both the numerator and the denominator. So I'll draw two parentheses here, and I'm going to try 4x and x for the first term split up for that trinomial, and then we'll try 3 and 3 at the back end. Then it's a sign of each, so plus and minus. If we check the inner product, we get 3x. The outer product gives us negative 12x, and that will give us negative 9x, so that looks like the right answer there. All right, let's try to factor the denominator then. It'll be 2x and x. And then we'll try an sign of each for the negative 15, so we'll do like a plus and minus. Then we can try 5 and 3 first and see if that works. So here we get 5x, and then we get negative 6x, and the middle term then is negative x, so that's correct as well. All right, good. So we factored the rational function, and we can see that there are common factors. So to write it in lowest terms, we'll cancel those terms out. Now, what happens here is we basically have what's called a removable discontinuity. What that means is that normally, if we have something like x minus 3 in the denominator, that would mean that x minus 3 is equal to 0 whenever x is equal to 3, right? And you'd have an asymptote here, a vertical asymptote at x equals 3. But because we're able to remove it or cancel it out, we won't have an asymptote. We'll just have a hole in the graph at x equals 3. So we're going to keep that in mind. There'll be a hole in the graph at x equals 3. Okay, from here though, we do need to be concerned with essentially where the intercepts are located. So let's talk about the first intercept. We would have an intercept whenever y is equal to 0 or r of x is equal to 0, right? And that would be an x-intercept. So we set y equal to 0, and then we say 4x plus 3 over 2x plus 5. Well, of course, the only time this is going to be equal to 0 is if the top is equal to 0. So let's just focus on the 4x plus 3 part of it. And if we go ahead and subtract 3 from both sides, we'll get negative 3 is equal to 4x, and then divide both sides by 4. We get that x is equal to negative 3/4. So at negative 3/4, or in other words, almost at 1, we have an x-intercept there. All right, now to find the y-intercepts, we're going to set the x values equal to 0. So if we did that, we'd end up with what? 4x would be 4 times 0 plus 3 over 2 times 0 plus 5. All right, and then from there, of course, these guys would cancel out, and you end up with 3/5. So the y-intercept is at 3/5, so maybe somewhere about here. Okay, good. So we have two intercepts plotted on the graph. Let's talk about the asymptotes now. Well, the first asymptote we're interested in is the vertical asymptote that will occur whenever the denominator is equal to 0. So in that case, whenever 2x plus 5 is equal to 0. That will happen when 2x is equal to negative 5, or in other words, x is equal to negative 5 halves. So basically at negative 2.5, so 1, 2.5, right here, we have a vertical asymptote. So I'm just going to plot this vertical asymptote here as a dotted red line. Okay. All right, so let's consider the horizontal asymptote then. We'll have a horizontal asymptote at y is equal to 4 over 2, or in other words, 2. And the reason why I know that is because the ratio of the leading coefficients in this rational function, right, is 4 divided by 2. And that's the case whenever we have equal degree for the polynomial in the numerator and the denominator. X squared is the leading term in the numerator, and x squared is the leading term in the denominator. So because the leading terms are equal, they have the exact same degree, we can say that the ratio of the leading coefficients becomes the horizontal asymptote. So y is equal to 4 halves, or 2. All right, so at y equals to 2, we have another asymptote drawn, this time a horizontal asymptote. All right, we can check now something about that asymptote. We want to see perhaps if the function is actually ever equal to the horizontal asymptote. It's possible to be equal to a horizontal asymptote. It's not possible to be equal to a vertical asymptote, but it is possible to be equal to the horizontal asymptote. So what we want to do is see if any place where the function would be equal to that. So let's try 4x plus 3 over 2x plus 5 is equal to 2. Let's see if this is possible. Well, that would give you 4x plus 3 is equal to 2 times 2x plus 5. And if you solve that, you get 4x plus 3 is equal to 4x plus 10. Well, that's not possible, is it? Because the 4x's cancel out here, and you'd end up having 3 is equal to 10, so not possible. What this tells us is that we know that the function will not cross or touch the horizontal asymptote, right? Whereas the line is not going to go through that horizontal asymptote. All right, so if we know that's the case, then our next step of the process is to go ahead and plot points on either side of the zeros and the asymptotes. So what we mean by this is we're going to look at a graph here, basically what we have laid out so far, and we want to think about, okay, what's going on between these intercepts? What's going on near the asymptotes, right? So we only have one x-intercept, so we don't have to do a whole lot there, but let's go ahead and plot some things near there. Like, for example, I might want to know what happens at -1 on the x-axis, right? That's very close to that x-intercept. I want to know what's going on over there. I also would like to know perhaps what's going to happen at -2, right? Because -2 is very close to the asymptote, right? On the other side of the asymptote there, the vertical asymptote, I might want to know what happens at -3. Those are good points, right? I also would be interested in what's going to happen at +1, right? And perhaps even at +2. And then I want to see what happens at +4. I'm not putting 3 in because I know that there's a hole on the graph at 3, and I know that we won't have a point there, right? Okay, to save us time, I'm not going to actually work out the arithmetic on each of these points. I'm just going to tell you what you end up getting if you put them in. So you get -1/3 for the first one. You'll get -5 minus 3 in the function is going to give you 9. If you get +1 in the function, you're going to have 1. If you plug in 2 for the function, you're going to have 1.2 roughly, repeating basically. So I'll just put 1.22, that's good enough for us. And then if you plug in 4 into the function, you get 1.46. All right, I'm going to actually plot 2 additional points now. I actually want to go all the way out on our graph, both to the far left and the far right region. So in other words, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is our biggest number on the upper side. So let's go ahead and put 11 in there. See what that gives us. 11 will give you only 1.7, right? Then let's go all the way to the left. This looks like we have -9 labeled there on our graph. Let's go ahead and do -9 and see what that gives us. At -9, you get the answer 2.5 approximately. Okay. So I have a couple of things drawn. Let's go ahead now and plot these points. If I do -1, -1/3, basically we're talking about something like there, right? And -2, -5, right? So 1, 2, 3, 4, 5, maybe that about here then. -3, we have 9. So at -3, we shoot upwards to 9. So that's going to be kind of off of our screen here. So I'm just going to kind of put it way up here, right? It'll be off of our grid because we have only 6 points labeled on that upper y-axis. Let's do 1, 1 now. So 1, 1. Then we'll have 2, 1.2. You can see it's very slowly increasing, right? Then at 4, we're going to have 1, 4, 6. So again, not even 1.5 really, so about there maybe. There's going to be a hole in the graph at 3, so I want to draw an open circle kind of there. And what I can see is happening here, I'm getting this kind of a shape, right? So I'm going to go ahead and run and connect this because from experience, I know we're going to get this asymptotic behavior, right? And I think the same thing is going to happen. We know all the way out at 11, we only get to 1.7. We're not even at 2 yet, right? We won't get to 2 because we know that that's where the horizontal asymptote is, and we don't actually ever touch that. So we know that this is basically going to carry on forever. So that graph is basically good on the right-hand side. We don't have a lot of things going on the left, but usually we see a similar kind of pattern here. So I only have one other point, which is -9, 2.5. So if I go all the way out to -9, I only get to 2.5, which is basically right about here, let's say. And we can plot a few more points if you wanted to. Like, for example, we could try -4 to see what that gives you, right? So let's go ahead and put in -4. This will be the last point I think we're going to work out here. So -4 gives you 4.33. And if you go out to 1, 2, 3, 4 and go up to 4.3, you're looking at something about maybe here, right? So again, what we're seeing is the same kind of asymptotic behavior. Remember, we have no point on the graph that actually hits y = 2, right? So we're getting something that shoots up in the air, right? And goes all the way out here on the negative end. So that's basically our graph. It's a good sketch of it. Don't forget to leave that hole where x = 3, and there's the graph of your function.